So as we start talking about vectors, we are now moving out of like one dimension movement, which is what we did before. In the chapter prior to this, we did, okay, they were moving in the same direction and they were going faster or slower, right? But now we're going to start talking about moving in multiple directions. And so as you can see here, the first question was, when does 3 plus 4 equal 5? Well, when we're talking about his movement 3 blocks and 4 blocks versus his displacement, which would be 5. All right, and so this should be very familiar. This should look like a right triangle. This should look like the legs of a right triangle, and the displacement should look like a hypotenuse, right? And so that's what we're going to start doing. We're going to start adding in multiple directions when we talk about movement. So when we think of vectors, we are going to think of not just a measurement, but the fact that there is direction. Some of this we have not talked about yet. We have talked about acceleration. We will talk about, and velocity. We will talk about force and fields and displacement. But those are examples of things that not only include a quantity amount, but also a direction. So they include multiple factors. Scalars, on the other hand, do not. And so when we talk about time, it's more of, you can think of, I am at a point in time. Yes, we can talk about something that has happened in the past. Mass, volume, these are just regular old measurements. Even temperature, even though temperature can be negative, we're not really talking about a direction of the temperature. We're actually just talking about a measured, right now, what is the current temperature on the scale that we are using, right? And so all of those are examples of scalars. It's just one piece of information that we've been given. There is no direction involved in those. So we're going to try to get through a lot of the terms and the notation so that you recognize these. We draw vectors as an arrow. So they are drawn as arrows on diagrams. So you'll look at the diagram that they have here. We have a couple of things happening with this tire. We have pressure coming up from what it's sitting on. We have pressure coming down based on how heavy that vehicle is, how much weight's in the tire, lots of stuff. We have a force going this direction because the engine is actually moving that tire going forward. And so when we look at a vector on a diagram, it's going to look like a ray, actually, if you think about geometry. You're going to have a starting point and you're going to have an arrow at the other end. The length of the vector, if we were to do this length, remember length is going to be an absolute value, so that's kind of what it looks like here. When you see a vector that you would draw, so like if I were drawing a vector, I wouldn't do boldface because it would be kind of hard for you to tell the difference between my bold-faced handwriting and regular handwriting. And so the other way that you could actually do it is to draw it with this little arrow on top, this little half-broken arrow on top. That actually also means a vector. And so that's what you'll see when you're like handwriting, when I'm instructing you, you're going to see that particular notation as well. Anytime you see the absolute value symbols, though, we are talking about the length of the vector, the length of the vector. And so that can relate to, we're going to talk about that in a little bit, but it's not just like measured length of it. It actually relates to some sort of movement that we are doing with that vector. Vector angles. All right. So when we are looking at vectors just in general, we have a couple things that we want to talk about. We have the tail, okay? The tail of the vector is the starting point, all right? So the tail of the vector should not have an arrow on it. The tail of the vector tells you where you are starting from, all right? Start of the motion, application of force, whatever this vector is representing in your problem, the tail is the starting point. And then the tip is the end where you see the arrow. That is the ending point of it. Unlike rays, so these are going to have a specific length, whereas a ray, by definition in geometry, goes on infinitely. Your vector does not. Your vector has a starting point and an ending point. The reason we have the arrow is different than in like math, where the arrow represents it goes on continually. The reason we have the arrow is so that we can indicate the direction of that particular vector, all right? Does that make sense? So if I were in Algebra 2 drawing a line, the reason I'm drawing arrows on the end of the line is I'm telling you, hey, this goes on forever. In physics, the reason we have the arrow is because I need you to know which direction we're starting from and which direction we're going with that particular vector. The length is proportional to the magnitude of the vector. So when you hear magnitude, you are going to think how long is this vector? Or sometimes it's going to relate to the velocity, how fast, or their speed. It depends on what you're talking about when you're talking about the magnitude. But when we're talking about the magnitude, we're talking about the length or how long this force happens. The next part, probably familiar with a little bit, angles can be measured in degrees and in radians. Hopefully we've already heard both of those terms. Angles can be measured in degrees or radians. Remember, radians is relative to the radius of the circle that you're talking about. All circles are 360 degrees. We use the 2 pi r to get our 2 pi as our distance around an entire circle. And so when we get into the trig review, we'll talk a little bit about radians, but that's how we measure them. We are also going to be talking about reference angles. This is something else that maybe in your math world you've heard before, but reference angles are always relative to the positive x-axis when we see the reference direction of these. I will say that there are going to be times when I go back to reference angle and it's not necessarily the positive x-axis, but it's the closest x-axis. So you can, when you're talking about direction for a regular old angle, we're going to do it the same way we would have done in a unit circle world. When we're talking about the reference angle, we're going to do the closest x-axis. So let's talk about how they give directions, all right? This should be in your handout. How they give directions. There's 3 different ways you can be given directions, all right? The first way is Cartesian angles. That word Cartesian should make you think of what? Cartesian should be a word you have heard before. Your Cartesian plane is your XY coordinate plane, right? So Cartesian plane, coordinate plane, that is just your XY axis that you have seen for years now. Here's what you need to know when it is just a standard directional angle. You are going to start, like it said, your reference point for a Cartesian angle is always going to be your positive x-axis, all right? Positive movement on the Cartesian plane is counterclockwise. Does everybody see that? 120 degrees positive, started here and went counterclockwise 120 degrees, all right? 120 degrees. Negative movement then, again, starts at your positive x-axis, but moves clockwise. That is a Cartesian angle, all right? So if I were looking at this though, my reference angle, here's what you need to know, the difference between your reference point. Reference point is your starting point of your angles, all right? That is the positive x-axis. Your reference angle is the angle that is made by your ending point, your ending ray there, and your closest x-axis. So in this case, if I were to look at the 120 degree angle, my reference angle would actually be the angle that's made from this point down to here. That would be my reference angle. So your reference angle is always going to refer back to that 180 degrees, which is over here, or your 360 degrees over here, okay? So my reference angle for the 120 would be 60 degrees because that's how far away I am from my closest x-axis. You're gonna look at whatever quadrant you're in. I am in quadrant 2 here. I'm gonna go to the x-axis that meets up with that quadrant 2, which is this x-axis. If I'm at 120, to get all the way over here is 180, which means the reference angle there is going to be 60 degrees. 60 degrees. Your reference angles will be between 0 and 90 degrees. They have to be, all right? Not inclusive because 0 is not going to have a reference and 90 is just going to be 90. So your reference angle is always going to be between 0 and 90 degrees. So then if I were to look at this negative angle here, negative 30, that's in my 4th quadrant. The closest x-axis is right here. So my reference angle for the negative 30 is just 30 degrees. Just 30 degrees. The reason you're going to want to know this is when we start doing the trig functions of my angles, you're going to want to use your reference angles so that you can do some vector addition and keep up with it. All right, because your calculator is going to spit out your positives and negatives however it gives it to you. But your direction may change and you have to know those particular angles because the only one that's going to help you is Cartesian. Cardinal directions and map directions, you're going to have to know those reference angles to be able to plug those in and use your trig functions. All right, let's look at cardinal. Cardinal directions are, you can think of if someone were giving you directions, not that a lot of people use south, east, north when they're giving you directions, but if you were to be navigating or something like that, then they're going to use navigation terms. They could either use cardinal or map, depending on what they're telling you. So cardinal is going to be when they actually tell you an angle in reference to a north, south, east, and west. All right, that's your cardinal. So if you look at this, hopefully you know your north and your south and your east and your west. If you don't, you need to learn them, right? Cardinal directions, 70 degrees south of east. Well, here is east. South of east is down. So this is where 70 degrees south of east would be. All right. What's nice about that guy is my reference angle for him is going to be exactly what they gave me. 70 degrees. That's how far away I am from my closest x-axis. Here's where it gets a little tricky. When you're plugging these into your calculator, 20 degrees east of south, you cannot use 20 degrees because your calculator is always going to refer back to the reference angle. So if you put in 20 degrees, it thinks you're 20 degrees away from your x-axis. You're not, right? So for this one, 20 degrees east of south, I am again at a reference angle of 70 degrees. So if I were trying to use this angle, 20 degrees east of south, to calculate something in my problem, in my calculator, I would have to put 70 degrees. I would have to put 70 degrees there. Does that make sense? Your calculator is always going to assume you are in standard form. Always assume you're in Cartesian form. Let's look at your map direction. Map direction. So this is the one that I think confuses people the most, all right? For map direction, so for cardinal, you'll notice that the movement just depended on what they told you, right? So for Cartesian, it's always starting at the x, counterclockwise, unless they tell you negative, right? Which they usually don't. Cardinal, movement, it just depends on what they told you. South of east, 70 degrees, and east of south, 20 degrees, were actually the same exact angle. So it just depends on how they tell you to move as to what you're going to do. For map, it is always the same direction, but you start at due north, all right? So for map, you always start north and you always go clockwise, all right? You always start north. So this is going to flip how you think of where you are, all right? So if I'm going due north, 90 degrees would be due east, 180 degrees would be due south, 270 would be west, right? And so my map is going to start north and go clockwise always. So if I look at this one, this is 215 degrees, but this is map angle, all right? So a couple things here. A lot of times when they give you map, they're gonna say it's a true movement, which means it's based on true north. And so instead of giving you degrees, they're actually gonna just give you 3 numbers. So let's say it's 70, 0, 7, 0, and then they're gonna put a T after it. So for 215 degrees, sometimes you will see it written just like this, 215 with a T. And that means we start at true north, we go counterclockwise 215 degrees, all right? Now here's the thing, calculating these are a little bit trickier because your brain is set on a Cartesian plane at this point in your math world. And so now you have to think about how I've moved. And if I were putting this into a calculator, I have to imagine my XY axis here, right? And I have to figure out what my reference angle is if I'm going to put this into a calculator. And so I have gone 90 and 180, and I'm actually seeing how close I am to the 270, which is over here now, since I'm starting at true north. So to find that reference angle, I would actually subtract from 270. All right? And so what would my reference angle be for this one? So my reference angle for this one is just going to be 55 degrees. Again, this is what your calculator is going to think. If you put in 215, your calculator will think that you started at the x-axis and went counterclockwise, right? And that's not what you did for this. You started at true north and went clockwise. The first one it gave me was just 205 degrees. If they don't give you any other information, you're going to assume a standard or a Cartesian angle, okay? And so if I have a Cartesian angle that is 205 degrees, I am going to start right here on my x-axis, positive, and I'm going to go 205 degrees. So remember, each quadrant is 90. That's going to be 180, and then I'm going to be 25 degrees. So if I'm sketching this guy, I'm going to sketch him about there, which means I went 25 past my x-axis. So my reference angle here would be 25 degrees. Cartesians are going to be the easiest ones to figure out your reference angle for. So fourth quadrant here, if I'm between 270 and 360, I can take 360 and subtract my angle. And so first quadrant, if you land there, your reference angle and your angle is the same. This is only for Cartesian, only for Cartesian. Here, second quadrant, you're just going to take 180, subtract your angle. Third quadrant, you're going to flip that, angle minus 180. Fourth quadrant, 360 minus angle. And then you will get to that reference angle. All right, that is only for Cartesian. Everything else, you need to just pay attention to where you are. 25 degrees east of south. All right, so first of all, you must know north, south, east, and west. All right. The part after the of is your starting point. So south is where I'm going to start. I'm going to start south here. East of south. Well, east of south moves this direction. So I'm going to move this direction at an angle of 25 degrees. So that is 25 degrees east of south. East of south. All right, east of south. Here's the thing. This reference angle, this type of direction, you're not going to have anything set in stone, okay? We just need to know how far away we are. But each quadrant is how much? Each quadrant is 90. So this whole quadrant is 90. I can just subtract it from 90. So 90 minus that 25 degrees is going to give me what as a reference angle? It's going to give me 65 degrees. So you'll notice it says 130 true, okay? 130 true. All right, this is a true north movement, which means when it's like this, I'm always going to start at true north, which is right here. This is my starting point right there. 130 degrees then. I am going to move 90 degrees, right? And then I'm going to move how much more? Yeah, about 40. That's probably too far. That's about 45. 40. By calculating this one, I actually already know what my reference angle is. How far past my x-axis did I move? 40 degrees. That is my reference angle. That is my reference angle. So go ahead and try the 130 degrees, 40 degrees east of north, and 190 true. So on this last one, the T means you're going to start north and go clockwise. So 190, I would have gone 90, 180, and then another 10. So my reference angle is, I've only moved into this quadrant 10 degrees, but I need to go all the way here to get to my reference angle, which would be another 80 degrees. When I'm looking at these three, so these are going to involve like planes traveling and all this. If I were to stop an object right here, would the value of the horizontal movement, from my origin be positive or negative there? And I'm asking it that way because I want you to think about it. For right here, would my horizontal movement, what is my horizontal movement? My x-axis. So my horizontal movement from the origin, is it negative or positive right there? My horizontal movement. X value would be negative. What about my y, or my vertical movement? What would my y movement be here? Positive. That's my vertical movement. So if I am thinking from the origin to get to this point, I would have had to move left, right, and up. Left, negative horizontal movement, up, positive vertical movement. All right? So for the second one, if I were to stop an object right here, horizontal movement and vertical movement, also positive, right? Those should be matching my coordinate planes, right? Let's look at this last one. If I were to stop an object right here from the origin, my horizontal movement is negative and my vertical movement is negative. All right, and so that's how we're going to start looking at these when we start looking at word problems. We're going to not just look at how they moved and how far they moved, right? We're going to look at where they ended up after moving there. So, for example, if I were to say an airplane traveled 190 degrees from true north at 255 miles per hour, that means starting here, it went 255 miles per hour along this line right here. All right? And so if we stopped him after a period of time, we would know how far he had gone and his location. All right, so a couple things about vectors. Vectors are only considered equal if they have the same magnitude and the same direction. Magnitude meaning how long, and direction meaning which way they're going, right? So in this particular example, your vector A equals your vector B. They are equal vectors. They are the same magnitude, which means the length of it, and they are the same direction. They start here, go here. It does not matter that they're sitting on top of each other. It just matters that they have the same length and they have the same angular direction. So if I were to draw kind of an axis there, right across here, the angle from that axis up is the same. That's what we mean by direction. So the same direction means it started here and has the arrow going this direction. The angle is the same and the length is the same. Those are equivalent. Those are equal vectors. So then if we wanted to move them to translate a vector, think about the word translate from geometry. It is when we move it from one location to another and we maintain its magnitude and its direction. We maintain its magnitude and its direction. So if I were to take this particular ray up here at the top, this particular vector, I can slide it down, I can slide it over. I have not changed its length or its direction, right? So just because I'm moving it around, I can move it anywhere on here. As long as I don't rotate that from the angle it's at, and as long as I don't change its length, it is still considered translating a vector, and they would be equal vectors. They would give you the same result if I were to put it somewhere, okay? And so that's what translating means. They have to have the same, it keeps its magnitude and direction, but you can move it from one place to another. So then when I'm adding vectors, what we're going to be doing is we are going to position the tail of the second vector on the head of the first vector. So what you'll notice is I have one vector, A, vector W. If I want to see the displacement of that, I'm going to put it all the way here. And I'm going to say, well, if I started at the beginning of A and went straight to the end of W, I would see my overall displacement from where I started. All right, that's how we add vectors. That's how we do the displacement. And so the example that they give you in your book is we have movement of a whale that's being tracked. And so they said, well, it started out here and it went, I'm going to say, let's say this is like 10 degrees south of west. All right. Then it moved, let's say 30 degrees west of north. Well, the way they have drawn this doesn't really help us that much. But if I were to put this over here, you could see the movement better. And if I wanted to know how much it was displaced from where it started to where it ended, I would say, well, it started here. Why is that so thick? I don't want it that thick. It started there and ended at the other end. So I can just say, well, it started here, and we can go straight across to there to figure out the displacement from where it started from. And so that's what we're going to be doing when we start adding vectors. We're going to take it from one spot to another based on how much it moves and where it's going. And we want to calculate, well, how far is it from its original destination? Not just distance, though, angular movement as well. Angular movement as well.